Okay, so let's continue. So last lecture we were looking at model of a diode, and what is the conclusion so far? So if I take a diode, how should I look upon a diode? What did we learn? How should I look upon a diode? So one thing is that the diode has an exponent. If I'm looking at is an exponentially current I equal to diode current ID equal to IS e to the power VD by N VT minus 1. So that's one aspect of it. If it is DC, then this is okay, right? So we said we could represent it maybe by a voltage dependent, say, current source. This is our current source ID. ID depends on VD. That's one aspect. Then if you have time varying, so DC is fine. If you have time varying signals, then you need to add a capacitance to it. We add a capacitance Cj. And what is the expression for Cj? Cj0, 1 minus Vd by Vbi to the power m, right? All these m and all that will be given to you. So that's one. And so this is in forward bias, and what you need to add is one more capacitance here, which we are calling it C diffusion, and C diffusion is ID by if I have n, then ID by NVT into a factor called tau, right? So that sort of completes the model for, at least a reasonable model for a PN junction diode under forward bias. And so the parameters for this particular total parameters are IS, then there is N, then there is Cj0, then there is M, there is Vbi, and then there is tau. Then there's tau. All these parameters are required. Before you can use a diode, you need these parameters. And note that, for example, to calculate C diffusion, you need ID. ID is the DC current flowing through it. Similarly, to calculate Cj here, I need the DC bias around this diode here, VD, whatever is the bias here. All right. Okay. A lot of problems we said we solve where maybe signals are either DC or they're low frequency. If they're DC or low frequency, we said we can take our diode and we can model it as a simple battery, this thing, and many times we said we assume it to be 0.7, but of course that value depends on the nature of the diode, the current, and all that, right? So many times this particular model we assume to be valid. As I said, if the voltages are very large, maybe you can even think of a diode in forward bias as a short. You could even think of it as a short. Okay, so even that is okay. So that's in the forward bias case. In the reverse bias case, we see that the current is very small in the reverse bias case. So we should model in reverse bias case, reverse bias diode. We should think of diode as simply a current here. Note that the diode is like this. So there's a current practically constant, IS, and if things are time varying, we include this capacitance Cj. That's it. So we think of a diode as long as the voltages are less than the breakdown voltage. V reverse bias voltage is less than the breakdown voltage here. So that's how we think of the diode in under the reverse bias case here. Okay. All right. So there are other situations also that we need to look at. Let me go to here a different situation. Let's take a diode. Let's take here and here, and let me add a 5 volt here, 5 volt, 1K here, and we ask ourselves, what is the voltage here? What is the voltage here and what is the current here, right? We have been asking that. So in this case, we said that because it's 5 volt, one could assume the diode to be about 0.7 volt or so, right? So if we solve it in if you're looking for an approximate answer, you'll say V0 equal to approximate, put up approximate sign, you'll say V0 equal to 0.7 volt. And of course we said current, then we can find out current is equal to 4.3 milliamperes. All right, so that we said we can do. Okay. Now let me add this, that this is 5 volt. Now let's think about it. Suppose this is 5 volt and this is V in. I make V in goes from 5 to 6 volt. 5 to 6 volt. And I want, obviously if V in is increasing, current will increase, and the diode drop will also increase. I want to know what is delta V naught. What is the change in V naught? V naught will change, you will all agree, because I've applied a higher bias, 6 volt, more current. V naught would be, if V naught were really 0.7 earlier, it would become a little higher. The question is how much higher. So obviously I cannot say here, I cannot continue to say because of the problem. Note that problem. Problem is asking how much is the change in delta V naught. You cannot say change in delta V naught is 0. You cannot just continue to say the diode is 0.7, it will continue to be 0.7. Remember, 0.7 was an approximation. So how much is the change in delta V naught? How do we find this out? So we want to find a change in delta V naught. So this would require us, if we really want a change in delta V naught, remember then we have to use not 0.7, we'll have to go and do a full model here, Vd equal to Kt by Q ln 1 plus Id by Is, right? We'll have to go there. Otherwise, what is the source of a change in V naught? We can't get that, and we'll have to go to this particular model here. But we know that to go to this particular model, you'll have to do iterative problem solving, right? Iteration, you'll have to do 1, 2, 3 iterations and all that, and then you'll have to get the value that that you desire, right? We don't want to do that. So my point is, there are many times in the circuit analysis, what happens is you've already analyzed the circuit. Let's say for 5 volt we've already analyzed. We have obtained 4.3 milliamperes. Now the question that is being asked is, if I increase V in by 1 volt, what would happen? Right? So we are talking about a new kind of analysis, which we call as, understand this, which we call as incremental circuit analysis. We're calling a new kind of analysis. Incremental. Normal analysis is what? In normal analysis, you'll say, well, what is the relationship between I and V and things like that, right? Between voltages and currents. Some voltages are there, you want some output voltage how is output voltage related to input voltage. That's a normal analysis. In this case, incremental circuit analysis, what we are interested in is due to some change in input, let's say, due to some change in input, what is the corresponding change in current or corresponding change in delta V naught? That's why the word incremental. You're not talking about absolute value. What is the absolute value of current or what is the absolute value of voltage? What you are asking is, due to some change in the circuit, what is the corresponding change in some other variable? Delta I, delta VD and things like that. That's why the word incremental. You're talking in terms of change now, not the absolute value. What is the corresponding change? Okay, so you're talking about change. And this is important because you've designed something, you're not happy with the design, and therefore you would like to change some voltage, some element and things like that, and you want to know what is the corresponding effect. So you would like to know what happens if you change this or change that, what happens to the output. You are interested in this. It's a lot of times we are interested in this circuit analysis. Sometimes you are interested like this. Sometimes what happens is, well, you have a circuit like this, and maybe now you've already analyzed the circuit. Maybe I introduce one more voltage source, an additional voltage source to my circuit. And I want to know, due to this additional voltage source, what will happen. As an example, let me give you this circuit here. Say I have a circuit like this, right? Circuit like this, and I have a diode. Same circuit that I'm drawing, say 5 volt, 1K, and like this, right? So I have this circuit, I've already analyzed everything. Now I am adding an additional voltage here. Let's say an additional voltage here. And this time I add a sinusoidal voltage, Vs through a capacitor C. And this is V naught. Right? And let me, just for the sake of it, let me put a resistor here also. Say 1K here. Okay? So what we are saying is, now, remember this part of the circuit, you've already analyzed. This part of the circuit you've already analyzed. Right? We've already analyzed. Now what I do is, I add another part to the circuit here. Another part here, right? I add another part here. I add an additional source. And then I'm asking what happens to V naught. So V naught, remember, was earlier some 0.7. We had all analyzed it. So in addition to 0.7, what do you think will happen? So before this additional voltage source, it was 0.7 roughly. Now, when I add this additional signal here, what do you think will happen? And this is sinusoidal. So what do you think will happen? It will acquire some sinusoidal signal, A sin omega t. This will be the additional signal here. Right? So what are we asking? We are asking what is the change in the diode voltage as a result of some change that you have caused in the circuit. You've introduced an additional voltage here, and you're wanting to know what is the change in the output. Again, what are we talking about? We're talking about incremental circuit analysis. Incremental circuit analysis. We are talking in terms of change. This is the change that I've introduced, Vs. I've added an additional voltage, and I'm asking what is the now corresponding change in the diode voltage, or a corresponding change in the current. There is a corresponding change in the current also. Current earlier was 4.3 milliamperes. Current would be some 4.3 plus something else also. So there's going to be a change there. And this is the question that we are asking. Incremental circuit analysis. Okay? Which gives us relationships between changes. The incremental, it could be anything. This increment that I'm talking about, it could be a DC voltage. It could be an incremental DC voltage. For example, in 5 volt, I could have added another voltage here, let's say maybe, and said this is 0.5 volt. I've added a voltage somewhere. It could be a DC voltage. It could be an AC voltage, like I've added here, an AC voltage here. It could even be incremental circuit analysis. It could even be, if I call this resistor R, I could even say, what if the resistor R changes by an amount delta R? You know, it's no longer 1K, but delta R is 0.1K, which means this resistor R that you see has become 1.1K. What is the effect on the output voltage? What is delta V naught? And I'm interested in what is delta V naught? Where is the corresponding delta V naught? So these are all of interest. Incremental circuit analysis, right? So this is of our interest. So now if you recall, how was analysis done? Analysis was done, what was our general, how do you do analysis? You apply KVL, KCL, and what else do you do? What else do you do? Model. Models of elements. Right? So a resistor, we said, is equal to V, model is V equal to IR. Diode, we saw that. Capacitor is I equal to C dV by dt. Right? Capacitor is ICV by dt. And like that, we have models where we have seen for diode and all that. We have seen here. Diode model, I equal to whatever. We have seen this here. So analysis requires KVL, KCL, and models of elements. Now suppose somebody is doing incremental circuit analysis. What will you require there? Incremental circuit analysis. Of course you'll do KVL, KCL are always there, right? What else would you require? What else would you require? You would require a model, right? You would require a model, but what kind of a model now? What kind of analysis are you doing? Incremental. So what kind of model will you require? Incremental model of elements. That's what you would require, incremental model of elements. Of all the elements, you require an incremental model. Right? Once you have that, then you can do the circuit. What do I mean by an incremental model? Let's explore this in more detail. Take a resistor. Right? We said resistor V equal to I multiplied by R. That's a normal model. Incremental model is what? Changes. Incremental. So a model, remember, a model is what? A model is nothing but relationship between voltage and current. So incremental model would be what? A relationship between incremental voltage and incremental current. What would be? What do you think will be? If I change the voltage across it, the current will change. What do you think is the relationship? Delta V is equal to delta I into R. It's a linear relationship. There's nothing. Delta V is still delta I into R. So incremental model of a resistor is what? Incremental model of a resistor is nothing but a resistor. Is nothing but a resistor of the same value R. Right? Same relationship. Delta V is delta IR. There's no change. Correct? There's no change. Incremental model of a resistor is a resistor of the same value R. Trivial case here. What do you think is the incremental model of a capacitor? I equal to C dV by dt. If I change voltage by a certain amount, the current would change. Delta I C d by dt. Or if you want to do it like this, delta V. What do you think is the incremental model of this? It's just capacitor is the same. Right? It's a capacitor C. Nothing changes. Incremental model of a capacitor is a capacitor. These are trivial cases. So a resistor remains the same, capacitor remains the same. Well, if you're thinking everything remains the same, that's not true. Say a current source. Somewhere you see a current source. Current source. Fixed current source. What is the incremental model of a current source? What do I mean by this? The current source means I equal to constant. Right? I equal to constant. Incremental model means what? Change in current, right? Delta I means 0. I is constant, which means delta I is 0. So which means a current source becomes what? What is the model of a current source when you're doing incremental circuit analysis? Open circuit. So current source, this becomes open circuit. If you are doing incremental circuit analysis and you see a current source, what are you going to do to the current source? Open it. Well, similarly, so current source becomes open circuit. Suppose I have a voltage source. Voltage source. So voltage source means what? V equal to constant. It means delta V is 0. It implies what? Short circuit. It implies short circuit. Are you saying that in incremental circuit analysis, voltage sources become short? Voltage sources become short. Current sources become open circuit. Okay? Well, suppose there is an element. Let me give you a hypothetical element. Some element is there. Okay? This element is there. So there is a current I and there is a voltage V. And suppose I say the characteristics of this element is I equal to K V square. Some element I equal to K V square. For example, let's say if I look at a transistor MOSFET where this gate and drain shorted together, may give you something like this. I equal to KV square. You know, MOSFET could give you something like this. If I take a MOSFET and I short this gate, it becomes a two-terminal device and something like this here. MOSFET will give you ID equal to K VG minus VT square. Something of this sort. Okay, so it's not entirely hypothetical. Elements like this are there. Now suppose you see an element like this. What would be an incremental model? How do I find incremental model? What is incremental model? Is the change in current due to a change in voltage. So what I do is, I change my voltage here by some amount. So first of all, now note that what I say is, the original voltage is, let's say, original voltage is V naught, initial voltage, or VI if you would like. Initial voltage VI, and I'm going to change voltage by a certain amount, delta V. This will be here, and the current is going to change I initial current plus some delta I. Correct? That's what happened. I changed the voltage by delta V and the current changed by delta I. And what are we looking for? What is an incremental model? The relationship between this change and this change. That's what we are looking for. We are looking for this relationship between delta I and delta V. Knowing that there is already some current flowing through the diode, through this element, there's already some voltage applied here, right? I'm looking for this relationship between this change. All right, so that's, I can do that. Delta I equal to K VI plus delta V square minus I, if I take it here, which is nothing but V square, can be written like this here. So this is equal to K VI, so K VI VI plus delta V minus V, so that's here. Sorry. So what do we get? K VI plus delta V, so we get K Vi plus delta V minus Vi, so K delta V multiplied by 2 Vi plus delta V, right? So we get delta I, so that's what we get, delta I equal to K times delta V multiplied by 2 Vi plus delta V. That's the model that relates delta I to delta V here, right? Now note that in this case the model depends on what? The model depends on the previous value. So it depends on now the bias point. Are you saying? The incremental model depends on the bias point. Where was the device initially biased? At what value of voltage was it biased? The concept of a bias point has come. The incremental model depends on the bias point. The initial bias point. Because you're changing things around the bias point. Whenever you say, I'm changing something, you're changing something around something, right? Say, I'm causing this change delta I around I. Initial current was I. And then I'm causing a change, right? So the concept of a bias point, it comes in here, right? What is the initial bias point? So my model depends on this. Delta I is K delta V into 2 Vi plus delta V. Now, if you note, the nature of this element is what? It's nonlinear, right? I equal to KV square, nonlinear. Incremental model is also. Note that the first term is linear, but the second term is delta V square. So the model is also nonlinear. And what is the problem with nonlinear model? Whenever I encounter a nonlinear model, the analysis becomes complex. The analysis becomes complex. But fortunately, what happens is we are saying incremental circuit analysis. We are saying incremental circuit analysis. Many times, the incremental that you see is small signal. Small signal incremental. I mean, it is incremental, but it's small signal. I'm talking about changes, but the changes are small. Now, when changes are small, if you go back, we were writing that delta I is K delta V multiplied by 2 Vi plus delta V. That was our model, incremental model. But if I talk about small signal model, small signal, note that whenever we talk about small signal, it's always incremental. Okay, small signal is a special kind of an incremental model where the changes are very small. It's a special type of incremental model where the changes are small. So small signal model, what approximation do you think I can make? When I say small signal model, what do I mean? The change here is much smaller than Vi. Vi could be 1 volt. And the change, what change have I caused? Maybe 10 millivolt, right? So example, Vi could be 1 volt. And the change that I'm causing is 10 millivolt. So in that case, what can I do? I can write this as delta I. Now let me add an approximate sign. Is equal to K delta V multiplied by 2 Vi. It's a linear model now. Note that it's a linear model. It's a linear model. This delta I and this delta V is a linear model. There's no square term, cube term, exponential term, nothing. So small signal models are always linear models. Why? Because the signal is small, and so all in if the signals are small, anything would appear as linear to you. Under small changes, everything is linear. No matter how a graph, if I take a graph like this, under small changes is always linear. Small changes wherever you are is linear. If you are here is linear. Small changes are always linear. I can approximate by linear. So small signal models are always linear. Now note, sometimes the delta I, we write it by a small I here to denote that it's a incremental change. I, small I. So small I equal to K small v multiplied by 2 Vi. Vi is what? Is the original value here. It's not increment. It's the original value here. So what does this relationship look like? I, relationship between small signal current and small signal voltage is what? A linear relationship. And so can I write this as equal to V by R? And what is the value of R? R equal to 1 over K 2K Vi. Note, very important results. I can write this as, look at this here, I can write this as here. I equal to K V 2 Vi. This 2 Vi is constant. Is some DC value or whatever it is some initial value. So I, relationship between I and V is linear, so I can write it as V equal to R, V by R, and R equal to 1 over 2K Vi. Right? So what are we getting? We are getting that this element that you saw, that element that I drew, some element, I equal to K Vx square, is small signal model. Small signal model. Small signal model is what? A resistor. A resistor. Small signal model is a resistor of this. R is R. And the value of R is equal to 1 over 2K Vi. And what is Vi? Vi is the bias point. Vi is the bias point. At what point is it initially biased? Because remember, never forget that small signal model is an incremental model. We are talking about changes. Never forget that. We are talking about small signal model is incremental model. Is incremental model. You're talking about changes in voltage and changes in corresponding currents. Always those changes. And when those changes become small, then you say, well, changes because then you start calling those incremental models as small signal models. And small signal models are linear, because all changes and all that can be related in a linear manner here. So note that I equal to KVX square. A small signal model is what? A resistor. A resistor of a particular value. A resistor of a particular value which depends on the bias point. Okay? Which depends on the bias point. Now, sometimes what happens is, we are saying, a small signal model we are building, we are asking what is delta I versus delta V. Sometimes this change that we are introducing, the small signal voltage, many times at least it could be an AC voltage. It could be a small AC voltage here. Right? The change that you have introduced into the circuit. So originally the circuit has only DC voltages. And now you introduced a change into the circuit which is an AC voltage here. And you're looking for what is the corresponding AC current or AC voltage elsewhere in the circuit. Okay? So this model then, sometimes people call it as a AC model. They tend to call it an AC model of an element. But remember, AC model is misleading. It's misleading. The correct word is small signal model. You've introduced a small signal into a device. So the idea is that, note that what is happening is that many times we have a circuit. Many times we have a circuit here, here, here. Let's say we have some circuit here, load here, and here, you know, some DC values and all that are there. Some circuit. Could be an amplifier circuit. You'll see why it is of interest in an amplifier. It's an amplifier circuit which is there. Right? The amplifier circuit is there. R. And so all this is, there's an amplifier circuit, all these are DC bias voltages here. This is DC here. Some voltages are applied. Right? Amplifier circuit that is there. And you know, some DC voltages and currents are flowing. Now, so this circuit is there. Now what we do is we say, well, this is input. Let's add an additional here voltage here, Vs. Right? We add an additional voltage here. Now what happens is, this was some DC value here, V0. It would acquire an additional voltage here, incremental voltage here. You have added an incremental voltage, so there would be an incremental voltage here. Incremental voltage here, V0. And in an amplifier, what are we interested? We are interested in V0 by Vs. That's the gain of the amplifier. You've added a signal here, and you know what is the additional signal that appears over here. So are you seeing that what kind of analysis do you have to do? Incremental circuit analysis. You've added an additional Vs, and you would like to know what is the additional V0. So you require an incremental. To get this, you require an incremental circuit analysis. You require an incremental circuit analysis. That's the one which will give you this. Now we say this incremental voltage is small. The incremental voltages that you've introduced are small. So it becomes not incremental, it becomes small signal circuit analysis. When the signals are small, you call it small signal circuit analysis. So small signal circuit analysis is an inherent part of an amplifier. Whenever you will make an amplifier, there would be some DCs and all that are there. And then on top of that DC, you add an additional signal voltage. And therefore you require to find out what is the effect of the signal on the output. You'd have to do incremental circuit analysis. That's the heart of doing an amplifier analysis or analog circuit analysis, right? And we are saying that this incremental voltages and currents are often small, so we call this small signal circuit analysis. And to do this small circuit analysis, what will you require? You require a small signal model. You require a small signal model. Of all the elements in the circuit, you require a small signal model. Of every element, you require a small signal model. What is a small signal model? It's an incremental model where the changes are small. Okay? Small signal model. So understand each one of these terms. Small signal model is what? Small signal model is an incremental model where this delta V and delta I are small. The changes are small. Now you may question how small. That's an important word, how small. Okay? This is an interesting thing. How small should it be? How small? Well, it should be, how small is decided by that my nonlinear elements can be considered as linear. The smallness is decided by that nonlinear elements non-linear elements can be considered as linear for these small changes. That's the criteria for these small changes. Non-linear elements should be considered as linear for these small changes. For example, the model that we had, remember, for this model I equal to, there was an element I equal to kV square. The incremental model that we built was delta I equal to K delta V 2Vi plus delta V. And then we approximated it as I equal to K, this delta, this is I, small I, this is small v, so I equal to K, 2Vi, this is constant, multiplied by V. We approximated it like this, I equal to K this here. How small should V be? Now you ask that question, how small should V be? How small should it be? Remember, where are you making the approximation? You neglected this term, right? So how small should it be? It should be much smaller than this term here, right? So V, how small is V? Should be much less than 2Vi, right? Much less than 2Vi. So if Vi happen to be 1 volt, then it should be, if Vi happen to be 1 volt, then this should be equal to 2 into 1 equal to 2 volt, much smaller than 2 volt. Now the issue is, what does much smaller mean? What does much smaller mean? How small? Again the question. Should I go? Is 0.2 volt small? 0.2 volt, if this is 0.2 volt, is 10 times smaller than this. Is it small enough? No? Or should I use, instead of 0.2, should I use 20 millivolt? 20 millivolt is 100 times smaller. Is that good enough? Who decides what is small? What is, what is this much smaller than this? Who decides it? Huh? Who decides it? How do you decide this value now? So from here we see that yes, the small signal voltage should be much smaller than 2 volt. How small than 2 volt? How much smaller than 2 volt? How much smaller than 2 volt? Well, remember, this is an approximation that you're making. What is the result of this approximation? Error. Every approximation will result in, the effect of approximation is, this will cause an error. This causes an error, right? So when you say much smaller, how small should I take? It depends on how much error are you willing to tolerate. How accurate an analysis you want to do, or how much error can you tolerate. If you can tolerate a lot of error, note that if I take V equal to 200 millivolt, what is the error? This is 2 volt, and this is, say, 200 millivolt, right? And I'm neglecting this. What is the error involved? Just neglect. This is 200 millivolt plus 2, and I'm neglecting this here. So what is the error involved? 200 millivolt versus 2 volt. What is the error involved? 10%. Right? I have 10% error. So if you're happy with 10% error, then 200 millivolt is okay. It's small signal for you. If you're happy with 10% error. But if you are happy with 1% error, you say, I want to do an analysis which is so accurate that 1% error has to be there. Then how small should I take this? 20 millivolt. Right? So this idea of how small should I take here? How small should I take here? That depends on how accurate an analysis you want to do. If you want to do very accurate analysis, you'll take very small. So normally in all of these analysis, we are quite happy with, reasonably happy with 10% error. You know, in this paper and pen based analysis, 10% error is okay. So in that case, I can use my model up to 200 millivolt. So what does small signal here means? That my signal across the element, small change across the element, delta V across the element. Note that this is important point. So what does small signal in this case mean? That this was my device, I equal to kV square, and what we are saying is small signal model. Small signal model implies that you know, for that V, delta V, sometimes we will write it as V, should be less than or equal to 200 millivolt. For error may be less than or equal to 10%. Right? That's what we are saying. That defines my small signal voltage. Now, a very common error that people make is the following. When they're doing this, suppose I have this element X is there, right? This element X is there. Suppose I have a circuit like this. This element X is there, and this R is there, and some voltage is here, and this is the incremental voltage here. Some element X, and we've connected. This is normal DC voltage here, and let's say this is the incremental voltage here. This is small incremental voltage here, V in. So the issue is, how small should V in be? To do this analysis, small signal analysis, how small should this V in be? Well, this V in will cause some voltage, small signal voltage across it. That small signal voltage should be less than 200 millivolt. Okay, all right, so let's do this problem here. Okay, let's do this problem. Let's take this, say this element X is there, and let's put some 1K here, and let's put some 5 volt here. Right, this element X is I equal to kV square. Okay, so let's for some hypothetical example, let's say for some value of K, the voltage drop, the current flowing is 1 milliampere, and obviously the voltage drop here is 4 volt. Okay, the voltage drop is 4 volt. 1 milliampere, 1 volt drops here, and all that. Now I'm saying, so this is the circuit that we've already solved. Okay, so you can calculate, you know, current is 1 milliampere, K equal K, and V is 4 for 16, so K is basically equal to 10 per minus 3 by 16. That's what it is. This circuit is valid for this value of K. Now, so this is a circuit that we've already solved, let's say. Now suppose what I do is I add an additional voltage here. Let me, not here, but I add an additional, let's remove this part here. I add an additional voltage here, a sinusoidal voltage, Vs, and I would like to know what is the change in V0. What is the small signal voltage here? Right, I added an additional voltage Vs. An additional voltage has been added, and as a result the output would become whatever was V0, which was basically equal to 1 volt. V0 was equal to 1 volt, and then there will be an additional V0 here, and I want to know what is this V0 here, and I know this Vs. Vs is some sinusoidal voltage. Let's say this sinusoidal voltage is 1 volt sin omega t. I want to know, can I do small signal analysis to find the answer. Let's do the small signal analysis. All right, small signal analysis to find out V0. So what we are doing, small signal analysis to find V0, that small V0. That's what we are doing, to find V0. Now remember, do not forget, small signal analysis is what? Incremental circuit analysis. So how do I do this analysis? I redo the circuit. I redraw the circuit where every element is replaced by is incremental circuit model. So replace every element by incremental model. And in case of non-linear element like this, what are we going to do? In case of non-linear elements, we replace by small signal model. We assume that the signal across it is small and we replace it by small signal model. So let's start by building the small signal equivalent circuit. So what are we going to get? We'll get a small signal equivalent circuit. We are doing a small signal analysis, so we'll get a small signal equivalent circuit. Equivalent circuit. Small signal equivalent circuit. How do we build a small signal equivalent circuit? Build a incremental circuit model for every element. All right, so let's start by this. Vs is a source, sinusoidal source. It remains as it is. That's my incremental voltage. What do I do to the DC? 5 volt DC. Incremental model of a DC is short. Okay, so we put a short here. We come here. So this is a short. Remember, this becomes a short here. Now, what do we do to the element X? The element X, we build this incremental circuit model, but under small signal assumption, so it becomes a small signal model. What is it? A resistor, R. And what happens to 1K? It stays as 1K and then back again. So this becomes the equivalent circuit, small signal equivalent circuit. This is our 1 volt sine omega t. But I have to find this model here, small signal resistance of this element. So how do I find that out? R was 1 over 2k Vi. So how much is it going to be? How much is R going to be? 1 over 2k Vi. So Vi was 4 volt, 1 over, so basically 2 into 4, 8, and k is 10 power minus 3, 16, so it is equal to 2k. So it's equal to 2k. If my calculation is correct, then it's going to be 2k, right? So you put 2k here. Okay? So we can find the answer, right? It's a simple voltage divider. This is 2k and this is 1k. So what is the drop across this? Drop across this is going to be 2 by 3 multiplied by 1 volt sine omega t, right? Drop across this element, and that's going to be 0.66 sine omega t. Now remember this model that I used, what was the condition? Less than, well, in this case it will not be less than 200, because remember it was 2 Vi plus delta V. So 2 Vi is 2 into 4, 8, so it should be less than 800 millivolt. And we do find less than 800 millivolt. So it's okay. Within 10%, this model is fine. Less than 800 millivolt, this model is fine. And then I get the answer. I get the answer that I'm looking for. But suppose instead of 1 volt sine omega t, it had been 2 volt sine omega t. Then this drop would have been, instead of 0.66, it would have been 1.2 volt, then I couldn't have used it. I can't use small signal analysis. I have to use some more complicated analysis to find out the answer that is there. Right? So are you seeing that small signal analysis, as I said, we will have situations like this here. We'll have a situation where we have a amplifier circuit with some DC values and all that are there here. And then what we are interested in is that if I apply a additional signal voltage, what is the corresponding change in the output? And therefore I have to do incremental circuit analysis in amplifiers. And as I said, the voltages and all that are often small, so that this incremental circuit analysis, we call it as a small signal circuit analysis. And this analysis is carried out by replacing every element by a incremental circuit element. So now you realize whenever you were doing small signal analysis, why were you shorting the voltage source? Why were you opening the current source? You're doing it because that's the model of a voltage source. Voltage source is short. Incremental model of a voltage source is short. Incremental model of a current source is open. That's why you're doing it. So then let's come back to, if you all agree, what is the incremental model of a diode? This is important. Incremental model of a diode. Or let me add more. Incremental is general. Let me add a small signal. That increment is a small signal. What is a small signal model of a diode? What is the small signal model of a diode? Now, how do I find small signal model of any element? What do I start with? Remember, the diode is what? Start with the diode. We're talking about DC or low frequency. So the diode is I equal to IS. And let's talk about first in the forward bias. E to the power VD by NVT minus 1. And in forward bias, we know that this term is very large compared to this. So we'll approximate, we'll say I equal to IS e to the power VD by NVT. This is reasonably okay. One can be neglected in forward bias. So how do I find, okay, let me add ID here. ID here. How do I find the incremental model of any element? What does it mean? It means basically that what is the change in ID due to corresponding change in VD. That's the relationship that we are looking for between delta ID and delta VD. That's the incremental model. That's the relationship that you're looking. So instead of doing expansion, what we can do is we can take this ID, and what we can do is delta ID by delta VD. Let's do this. Delta ID by delta VD will be equal to IS e to the power VD by NVT multiplied by 1 over NVT. Correct? If I take his derivative. Note that by taking delta ID by delta VD, by taking a differential, I've already taken it as a very small change. So this one, then I can write it as ID, small change ID, delta ID, or if you want, you write it as delta ID equal to, what is this? Capital ID NVT into delta VD. Right? Delta ID, I can write it as delta ID into delta VD. Correct? No problem. This one, you know, another terminology, I can write it as small signal ID equal to ID by NVT, small signal VD. This one, I can write it as ID equal to VD by RD. RD is NVT by ID. Important results. Small signal model of a diode is what? A resistor. Small signal model of a diode is a resistor in the forward bias. A resistor of value RD equal to NVT by ID. ID is what? The DC current or the bias current flowing through the diode. DC or the bias current flowing through the diode. So the small signal model is a resistor. That's the small signal model. How small should the voltage be? How small should the voltage be? Well, remember, if you look at this, when you did this here, right? Look at this term. Delta ID is IS e to the power delta VD by NVT. Right? If you were to expand this, what will you get? IS exponential 1 plus delta VD by NVT plus, you know, square terms and cube terms and things like that. Now, when we are doing small signal model, what are we doing? We are neglecting all these higher order terms, nonlinear. So under what condition will it be true? When this delta VD, it should be much less than NVT. Normally, if I take n equal to 1, then it's saying delta VD. So it's saying that this, you know, delta VD. So what it is saying is, what I'm getting is that this whole thing is valid if the small signal voltage VD is much less than VT for ideality factor of 1. That's what I'm getting. Delta VD is much less than VT, VD is much less than VT. So the small signal model of a diode is a resistor, and that model is valid only if the small signal voltage across the diode is much smaller than VT. And VT we know is 26 millivolt. So we are talking about, again, it depends on how accurate an analysis you want to do, right? So we are talking about 2 millivolt, 3 millivolt, 4 millivolt, the model should be okay. If you apply 20 millivolt, the model will be very poor model. So how small is, you can see from this relationship here, how small, which means you're neglecting all these terms here, square term and cube terms and all that. So we have now obtained something called, we are learning something called the incremental circuit model, incremental model of an element. We're learning also small signal model of an element. How small should the voltage be? We are seeing all of that, how to calculate that. Okay. Now, this is diode. And we said small signal model of the diode is a resistor R. So why don't you guys solve this problem then? The problem that we had raised earlier. Here is my diode. and here is a resistor, here is another resistor, here is 5 volt, 1k, 1k, and I'm adding a capacitor here, and I'm adding a source here, and I'm adding a source which is let's say 100 millivolt sine omega t. This is a capacitor C. This is also ground. What I'm interested in knowing is the sinusoidal voltage here. Sinusoidal voltage here. I'm interested in knowing that. How much is the sinusoidal voltage here? V naught, small v naught. How much is the value? Alright, so find this out. Now, the other thing is the input is a sinusoidal. Small signal voltage, I mean the incremental voltage is a sinusoid. The capacitor at that frequency acts as a short. C at whatever this omega is, C at omega is like a short circuit. Okay, just assume that. So the value of C, so we know that it causes an impedance 1 over omega C. So we are saying omega and all that is so high that this capacitor acts as a open circuit. Short circuit. So find out the value of this sinusoidal voltage V naught. So basically you have to do a small signal circuit analysis of the circuit, and as I said, for the diode, assume that the ideality factor n equal to 1. Don't ideality factor n equal to 1, and thermal voltage Vt assume 26 millivolt. Okay. right, how do I start? What do I do? How do I think about this problem?
Short 5 volts.
No, wait, before that. So what we are thinking is we are trying to solve this problem through small signal analysis. Small signal analysis, right? That's how we are trying to solve it. We are saying this voltage is what? The incremental voltage or additional voltage that we have applied, right? Is the additional voltage that we are applying. This is the incremental voltage that we are applying. Incremental voltage that is applied. The other voltages are not incremental, right? So the first thing to analyze is what is the circuit without the incremental voltage? See, incremental voltage is applied afterwards, right? And then you want to see what is the effect of this incremental voltage on the output voltage here. So first thing is remove the incremental voltage. Okay, so if I remove the incremental voltage, how do I remove a voltage here? If you remove the incremental voltage, so first is do the analysis without the incremental voltage. So if I want to do the analysis without incremental voltage, what will I do? What will I do to this source? Short it. I will remove this source here. I will remove this source here. I will short it. Okay, and then do the analysis. The source has been removed. Do the analysis. Find the current, find the voltage, everything that you do, find that out. So when you do the analysis, what else do you find? Well, then the only voltages that I have in the circuit is only DC. So capacitor doesn't matter. So all this goes away. Right? I'm left with this. Now what do I do? How do I solve this? This is 5, 2K. How do I find this current I? What do I assume for the diode? 0.7, let's assume. So we get a current I which is equal to 5 minus 0.7 divided by 2K, and this is equal to 4.3 divided by 2K. So that's 2.15 milliamperes. So that's the DC current flowing through it. And the diode voltage is how much? 0.7. VD is 0.7. Fine. So that's the first part that is there. You have to do the analysis before applying the incremental voltage. Okay. Then do an analysis which is incremental circuit analysis. Okay. So for that, what do we do? For that incremental circuit analysis, what do we do? So we keep this in mind, 2.15 milliamperes. We have to build a small signal equivalent circuit or an incremental circuit equivalent circuit. So for that, we go back and our circuit becomes less. The original circuit was, remember the original circuit was here and this one. This was the original circuit. So we build now, and so this part is complete. So we build an incremental circuit or a small signal equivalent circuit of this. So what do? We replace every element by a small signal model. So this is anyway an incremental model, stays as it is. Capacitor stays as it is. What happens to 5 volt? So this, we should take it out, replace it by short, start by here. Resistor stays as it is. This becomes a short. This stays as it is. Diode becomes a resistor. Resistor, and what is the value of the resistor here? RD will be equal to, you're right, this resistor, RD will be equal to, VT is 26 millivolt and ID is about 2.15 milliampere. So the resistance is roughly what? Maybe 10 ohms or what? 13 ohms or so? Huh? How much? 12 ohms. Alright, 12 ohms. Let's just take approximate 12 ohms. Okay. Now we said that the capacitor is such that at that frequency capacitor acts like a short. So let's remove the capacitor here. It acts as a short here, and let's add this here. So now what is the voltage at this node here? Vs is here 1K and 12 ohm. So it's basically a voltage divider. This one is a voltage divider. So the answer is the small signal voltage would be roughly 12 divided by 1K multiplied by Vs. Vs was 100 millivolt. So you can check here 12 divided by 1K, and this value is extremely small. It's extremely small, much smaller than Vt, and therefore our analysis is correct. And so we've obtained a value of the sinusoidal voltage. If I apply a voltage here, we've obtained the value of sinusoidal voltage at this point. V naught is that value. We have obtained that value, which is 12 by 1K into Vs. Okay, so that's the procedure now for doing a incremental circuit analysis. Very, very important analysis where you're looking for what is the effect of some change that you have introduced into the circuit. And then you want to know what is the corresponding change. And therefore, what you require is a incremental circuit model, or for nonlinear elements, you require a small signal model. Now, before we leave the diode, so we said that the diode is like this here, right? But this is okay, RD equal to VT by ID. This is okay as long as we are at a DC or low frequency. But if the signal, for example, if I have a signal here across the diode, right? Remember we added a signal, sinusoidal signal here. Say, if the signal across the diode is, frequency is high. Frequency is high. Then the diode, remember the diode was, we said the diode was here. A diode was here, plus Cj plus C diffusion. C diffusion. Then you have to take capacitors into account. If the signals are time varying, and especially if the signals are high frequency, then you have to take the capacitors into account. So then what happens to the model? Well, remember this source, this nonlinear current source became RD. But what is the small signal model of a capacitor? It's a capacitor, so it becomes like this here. Cj, and this becomes C diffusion. This becomes the small signal model of a diode. We will call this as the high frequency small signal model. And this is what we call as the low frequency LF small signal model. So depending on the frequency of interest, you may want to do a small signal or a low frequency or a high frequency. Now, how do you decide what is low frequency and what is high frequency? How will you decide that? Is 1 kilohertz low or high? Is 10 kilohertz low or high? 100 kilohertz low or high? How will you decide to whether to use this model, low frequency model, or to use the high frequency model? How would you decide that? As an example, let's say we just found out that this is equal to roughly 10 ohms, right? So let's say this is 10 ohms. Let's say I find Cj is equal to 1 pf. I calculate the value, we know how to calculate the value. And let's say we find that this value is 100 pf. This value, how do we decide this value? Let's put some let's for a moment just put some value, 100 pf. Okay, what would be low frequency and what would be high frequency? Is it easy to find out? In this model, what are you doing? You're neglecting capacitors, right? The accurate model is what? The lower one. It includes RD and it includes capacitances also. So it's more general as compared to the previous one. So when can you neglect the capacitance? If you look at this is 1 PF, this is 100 PF. So in forward bias, which is the capacitor which is important? Normally the diffusion capacitance is usually much higher, 100 PF. So how do I decide what is low frequency? Well, all that I need to do is calculate what is omega C, impedance of this. If this omega C, what should I do? If this 1 over omega C is much larger than RD, then what does it say? I can neglect the capacitor. I can neglect the capacitor. Omega C is much larger than RD. I can neglect the capacitor. Right? So all you need to do is, you know the value of RD, you know the value of CD. Just check if 1 over omega C is much larger than RD or not. If that is true, well, you can neglect the effect of your capacitors and then go ahead and use the low frequency model. If it is not, then you have to include this C diffusion and CJ and all that, and then do a more accurate analysis. All right. So before we conclude our diode, we are talking about models of element. Now model, we said, can be highly accurate, and could be very simple. Could be very simple. And you could have a range of models here. So I could build, for example, we could call it the accuracy. So I can have various kinds of models ranging from highly accurate to very simple. For example, we were discussing diode. What is the simplest diode model that you can think of in forward bias? Short. Right? And the highly accurate, we said, well, it is like this here, and capacitors and more capacitors and things like that, more accurate here. And in between you could have another model which is simply a battery and things like that, different models that are there, right? So highly accurate model is going to be, if I write this as complexity, right? A complex model in general is going to be somewhere here. Complexity is high, accuracy is high. Complexity is medium, accuracy will also medium. Complexity is low, accuracy is also of the model is low, right? Generally, right? Complexity versus accuracy. So if somebody asks you, if I have a highly accurate model, if highly accurate model is available, why bother with inaccurate model? Why should I bother with inaccurate model? Accurate model is available to you. Why do you bother with inaccurate model? So less complex. So what you're saying is the simplicity is also important. It's not just accuracy. Accuracy is important, but for you, simplicity is also important. So accuracy is good. You want accuracy, but you want simplicity also. Right? You want simplicity also. But if you use a simple model, then you get an inaccurate result. If you use a simple model, you'll get an inaccurate result. In fact, the model that I've built here, they can be more complex model than this. So the point is, simple model, fine. Simple, if you use simple, it will give you inaccurate results. And complex model is actually very difficult to use. You will not even be able to use it. Suppose I have a circuit consisting of 10 diodes. 10 diodes, okay? 10 diodes, and each diode is like this with a nonlinear current source. The analysis will become very difficult, design will also become very difficult. Right? But with the 0.71 volt model, you will be able to do it. So, accurate model, simple, but you'll get inaccurate results. Accurate, but complex model, you won't be able to use it. Would not be able to deploy it. You can't deploy it in a circuit consisting of one diode. Maybe you can do 5-6 diodes, you can't do it. So what do you do? If you have inaccurate result, your circuit is going to be inaccurate. It's not going to function the way you want it. You wanted 1 milliampere current to flow through your circuit. You use a simple model, you find 1.5 milliamperes is flowing. So what do? You have accurate models available. But accurate models are becoming difficult to use. Simple models are very easy to use, but they give me inaccurate results. So what do I do? Are you seeing a problem? Simple models are easy to use. Very quickly I'll apply it and get the answer, but the answers are wrong. If I build a circuit with it, the circuit will not function properly. An accurate model I'm not able to use. All these nonlinear equations with 10 diodes and all that. People are building not 10 diodes, people in op-amp. If you look at an op-amp has what? A 741 op-amp will have at least 25 transistors. Each transistor is nonlinear. Right? So if I start deploying all these nonlinear elements, I'll get into trouble. I'll not be able to do anything with it. So what do I do? What is the solution to this? I have simple model available to me and I have accurate model available also. Simple model very easy to use, but not very good result. And accurate model not easy to use at all. So what is the solution? This is not just in circuits, it's everywhere in engineering. This is a general engineering problem. You have simple models, you have complex models. They're always there. So what do I do? How do I solve this dilemma, this problem? How do I solve this problem now? Simple versus complex.
Minimize the product of
Huh?
minimize the product of accuracy and simplicity.
Minimize the accuracy.
The product of simplicity and accuracy.
No, you're right, but so two kinds of models I'm giving you, right? If you're thinking, let me give you an example. Okay, this resistor that you see here, right? In the lab, you've all seen a resistor, correct? You think it's really a resistor? It's a simple R. In the lab, if you pick up a resistor, this thing that you see here with all these bands and all that, and we say it's a resistor, right? We read and we say it's 2.2K, right? Do you think it's really a resistor? If I want to look at it accurately, what is it? It may be more accurate to think of this as, okay, 2.2K, but the leads and all that will have some inductance, and across between these two will have some capacitance. some L and some C. Now you may say, well, it may have very small C and L and all that. At some frequency, you know that omega L, as you raise the frequency, omega L becomes higher. And this capacitor, you may say, well, it's very small, but omega 1 over omega C is at some point, at some higher frequencies, this may become to matter here. So that simple element that you're saying is a resistor is not actually a resistor. It has inductors in it. It has a capacitance in it. Except that maybe you're working at a frequency at which this omega L is very small and capacitor is very, impedance is very large. So you say it's like a 2K. But for the sake of discussion, let's say I have a simple model. This is simple, correct? And what is the characteristic of this? This is more accurate, right? It includes inductance in it. It includes capacitance within it. It's all more accurate. So this is more accurate model, but more complex. Accurate, but complex. And this is simple, but potentially inaccurate. Now suppose I ask you to design a voltage divider circuit. I say design a voltage divider circuit. I have a sinusoidal source, 1 volt sine omega t, and I want here 0.5 volt sine omega t. I said design the circuit for me. Design the circuit for me. You say trivial. If I use a simple model, all that I need to do is put here, let's put something like 0.3 or whatever, something. I'll put some value of R1 here, R2 here. Design is very simple, right? Extremely simple design. Some R1, R2, and you will get the value 0.3 that you're looking for if I use a simple model. But suppose you use this model. What do you have now? RLC. Are you seeing that design is going to become more complex? You have RLC, design is going to become much more complex. You'll have a hard time figuring this out. Okay. So my point is, the point that I'm trying to say is that with the simple model, you can do analysis, you can do design, but it's going to be inaccurate. With a complex model, you can't even do it. It will become almost even, very difficult or almost impossible to do it. So what is the way out? Are accurate models useless? Huh? Are accurate models useless? Are accurate and complex models useless? Are they useless? All these people who are developing this accurate and complex model, they are all, it's of no use. Simulations can use this model, he's saying. Okay, what do we mean by that? Okay, what he's saying is simulation. So what he's saying is we can use the complex and accurate, complex and accurate models for simulation. Simulation of what? Simulation of circuit. Okay, for simulation of circuit. Yes, if I feed it into a computer program, that's easy to, for a computer, it's easy to write an algorithm, easy to handle complex this thing. But to simulate something, I have to give a circuit, right? Computer cannot simulate anything unless you give a circuit, right? So if I'm going to design, let's look at this problem here. Where do I get a circuit to simulate? How do I get a circuit first of all to simulate? If I'm given a problem that design this voltage divider, first I have to design a voltage divider. Then you're saying I simulated. Simulated to do what? Why do simulation? Yes, you can simulate. If you give me a circuit, here, right? If you give me this circuit here, some circuit if you give me, with some values RLC and all that, yeah, the computer will simulate it and will give you the result. Right? Will give you the result. But which circuit to simulate? And what do I do with simulation result? What do I do with simulation result? So you're on the right track. Simulation can be helpful. I can use a complex model in a simulation, correct. Manually, by myself, I may not be able to use a model, a complex model, but with computers I can use a complex model. Okay, how do I use this? How do we use simulation? How do we use simulation in design? Let's add this. Okay. How do we use simulation in design? The central task of you as an engineer is to design. The central task is not analysis. The central task is design. Analysis is a part of design. Okay? So how do we use simulation in design? What do we do?
We can design using simpler models and then feed it to computer and then check for the errors.
Okay, all right. So what he's saying is follow. Okay, let's explore that. What he's saying is, so let's say I have some specs, right? All design starts with specifications. For example, I want to create a voltage divider. So what he's saying is the following. I do a design, and the design is based on simple model. So simple model, specs are there, and I do a design, right? And I get a design here. I get a circuit, right? I get a circuit. Some specs are given. Say you have an amplifier design, an amplifier for voltage gain of 100, input resistance or something, and all that, all those specs that are there, frequency response and all that. You use a simple model, right? And you go through the design process. With the simple process, design process is okay. You will be able to design. You will be able to get a circuit, but the circuit is not accurate, right? The circuit will not be the right circuit because you use a simple model but inaccurate model. So the circuit is not going to be the proper circuit. So the circuit will have some problems with it. Gosh, this is now becoming a problem. So the circuit will have problems, right? So now what you're suggesting is that I take this circuit and I simulate it. I take this circuit and I put it in a simulator. Circuit simulator. Circuit simulator. And the circuit simulator, it will use what? Accurate model. Accurate models it will use. And the circuit simulator will do that, and I simulate it and I find the gain here, AV star. Right? So you were supposed to get a gain of 100, and you use a simple model. You design a circuit. Right? You design a circuit, you simulate it, and you get a gain, and the gain is not 100 because you use a simple model. The gain is 90 because there is inaccuracy in this circuit. Now what do you do? Fine, we found a role for a complex model. We'll use a circuit simulator. The circuit simulator tells us your design is inaccurate. Your design is inaccurate, is giving you 90. Now what do you do? What do you do? Well, you know that you wanted 100 and you're getting 90, right? You understand the circuit. Obviously, you have to understand the circuit to design. So you know the role of different elements, right? So for example, let's say I have a circuit like this, right? Remember this circuit here, this circuit and all that, RC. You know that, well, if I increase RC, the gain is going to increase. So what you do is you take this 90 here and you go back here to this design process. And you say, well, if I increase RC a little bit, the gain is going to go up. So what you do is in your design or in your circuit here, you increase the value of RC by a certain amount, and you go and simulate again. And you check, well, you find, well, it's 95. Then you increase some more and you find, well, it's close to 99.5. So you go through this iteration. You go through this iteration. So what you're saying is, I start with some specs, I use some simple model to design. The design is not going to be very accurate. I then simulate it with accurate models and I find the error. And because I understand the circuit, I go back to the circuit and I tweak it. You know, I tune it. I tune my circuit. I change some resistors, increase some value, decrease some value and all that. I tune it and then I simulate again. And I check again. And then by this process, 95 or 99.5, I tune my circuit to give me the gain that I want. Now you could do this tweaking and all that manually, but you could also write a computer program. You know, this is like optimizing. You know, optimizing the circuit. You could even write a computer program which will change the different values of resistors and capacitors and all that and optimize the circuit to meet this gain or not. Right? So now you are seeing that yes, I require a simple model to give me that initial design. I need that initial design. I use simple models to give me initial design. That's one. And also I need simple models in order to understand the design. Because without understanding, how would you know whether RC should be increased or decreased? Right? So simple models have a very important role. You require them to obtain the first initial design, and then you can tune the design through simulation, or also to understand. If you use a complex model, suppose I use a very complex model, right? I use a very complex model and AV equal to some big numerator, denominator and all that, some huge expression I give you. complex model. Would you understand anything? Will this be good for understanding at all? You won't make heads and tails of it. What does it mean, this big expression? How does gain depend on RC or R1 or R2 and all that? You won't understand anything. So you are looking for simple expression. You're looking for simple expression that gives you understanding. You want to understand how the circuit works. And so that you can modify it, you need simple expressions to understand it. And of course, then simple models too. And simple expression you will obtain from use of simple model. Only if you use simple model will you get simple expressions. Otherwise, you will not get. So you require that for understanding. So those 0.7 volt model and all that, they may not be the best models, but they give us very simple expression. And they help us understand how the circuit works. And they will also help you to give how the circuit works, and they will also help you to give the initial design. Initial design, which you can then later on refine it. You can later on refine it by using more complex and more accurate models through circuit simulation. So there's a role for both these models, accurate models and this thing here. So when I gave you this model here, you know, the diode model that we saw, this kind of a diode model, this non-linear current source and a capacitance here and a capacitance here. So these models, and sometimes a resistor is put here, and these models are suitable for mostly circuit simulators. That's where we tend to use here, okay? So now that you have a good idea about a diode, a PN junction diode, and the next thing is then to look at a BJT. Next thing is to look at a BJT. So now, what is it that you, okay, I think time is already up, so we'll take it up in the next lecture. So we have IC, we have IE, and we have IB. So let me just ask first, how does, we'll stop here, how does IC, we need to understand the bipolar transistor from a circuit designer's perspective. How does IC change with VCE? Does IC change with VCE? VCE, right? This is collector terminal, this is emitter terminal, this is an NPN transistor. How does IC change with VCE? What does it go like? You guys have seen this graph or not? IC increases with VCE, and then we draw another graph, right? And we draw multiple graphs here like this, right? What are these multiple graphs due to? We have multiple graphs. These multiple graphs, this is one graph here, this is another here, this is another here. What are these multiple graphs?
Corresponding to different
VBE, but normally, yes, but we normally say different values of IB. IB3, IB2, IB1. Different values of IBs. This is a plot. Does it make sense that we call it as the output characteristics of a transistor? Does it make sense? Output characteristics of a BJT. Normally, where do we take output from a BJT? At the collector. So this is like the output current, right? And VCE is what? The output voltage. Voltage is also taken between collector and emitter. So it's like the output current versus the output voltage. Output voltage here. Output voltage, and this is like the output current. That's why we call it the output characteristics of a BJT. Right? Two things are visible here. We can clearly see that there are two regions here. If I can just draw like this here. Two regions here. There's a region here, and then there's a region here. What are those two regions called? Which is saturation? This one is, we call it saturation. All this region where current is varying. And this region is where we call linear region. Although it seems opposite, right? Here it seems that the current is saturated. It's not changing with VC. But we don't call that saturation region. This is called, linear, or we also call it, actually more proper word is active region. Active region. This part of the transistor, we call it active region here, active region here. Okay? Now if you look at the active region is more important for amplifiers. If you look at the active region, what does it look like? What is happening in the active region? See? Current is flat. Current is independent of VCE. It's acting like, but it depends on something. What does it depend on? IB. So you think that between the collector and emitter, can I say that the transistor in this region is acting like a what? Current dependent current source. Current dependence. Current controlled current source. Current controlled current source. We write this as beta times IB. In this region here, in the active region, it acts like this here. Current controlled current source. But as somebody said, IB changes. Why? Because you change the base voltage. So you could also write it as, not only that, you could also write a bipolar transistor as a voltage controlled current source. Is related to, is some function of this current, is some function of base voltage, base emitter voltage here. You could also look upon it like this here, right? It's very interesting. So you have when you go to a transistor, you see that the transistor in the active region acts like this current control current source, or a voltage control current source here, right? Let's stop here. From the input side, the transistor actually looks like a diode. There is a PN junction here. It looks like a diode from the input side, right? It's a you know that the transistor, NPN transistor, we have N and P and N, and this is emitter, this is base, and this is collector. So between base and emitter, you see a PN junction. This is P here, and this is N here. So between here and here is a PN junction. It's like a diode. So when you look at the transistor from the base side, it looks like a diode. When you look at it from the collector side, it looks like a voltage control current source in this region. In this region here. In this region is more like, if you are here, maybe like some kind of a nonlinear resistor. But in this region, it's like a current source. And this is a very important region. So let's stop here, then we'll continue.